Okay, let's dive right into this. Welcome to the Explainer, where we are going to unpack exactly how sunlight magically turns into the electricity running your screen right now. We're talking a full-blown journey from massive solar grids out in the desert all the way down to the invisible quantum level. It's a pretty wild mix of engineering and physics, so let's get into it. Now, here's a really wild core mystery to start us off. Did you know that when you hook a solar cell up to a power supply, it actually emits infrared light? You can't see it with your naked eye, but cameras without filters can totally pick it up. It's basically running in reverse. So that kind of begs a huge question. If a solar cell absorbs photons to make electricity, and an LED emits photons when it gets electricity, what happens if we feed photons back into an LED? Like, could an LED actually power itself? Keep that in the back of your mind as we go. But before we get too far ahead of ourselves, what does photovoltaic actually mean? You hear it all the time with solar. Well, it's actually a perfect mashup. Photo literally just means light, and voltaic means voltage. Put them together, and it is simply the phenomenon where light from the sun interacts with microscopic particles to create a measurable electrical voltage. Simple as that. All right, moving to section 1, anatomy of a cell. If you were to slice a solar panel open, you'd see it's basically a highly engineered sandwich. At the very bottom, you've got a solid conductive metal backplate. Sitting right on top of that is the absolute star of the show, the silicon semiconductor layer. Now, raw silicon is super shiny, and we definitely don't want sunlight just bouncing off it back into space, so they slap on an anti-reflective coating. Next comes the metal grid, thicker bus bars and these incredibly delicate little metal strips called fingers that literally reach out across the silicon to grab free electrons. Finally, the whole shebang is topped with heavy-duty protective glass to keep it safe from the weather while letting all that good light in. Which brings us to section 2, the quantum physics. To really understand where those electrons are coming from, we have to zoom way, way in, down to the atomic level. Silicon is our base semiconductor, and it has a very quirky personality. A single silicon atom has 4 electrons in its outer shell, but it desperately wants 8 to be stable. So what does it do? It forcefully links up and shares electrons with all its neighbors, creating this perfectly rigid, locked-in grid. It's totally stable, but completely unmoving. And as you probably know, without movement, we don't get electricity. So we have to cheat a little bit. We manipulate the silicon by mixing in or doping it with other elements. On one side, we bake in some phosphorus. Phosphorus has 5 outer electrons, so suddenly we have extra unattached electrons floating around, giving us a negative charge. We call this N-type silicon. On the flip side, we add boron. Boron only has 3 outer electrons, which creates these literal empty spaces, or holes, giving that side a positive charge. That's our P-type silicon. Now, when you smash these 2 layers together, they form what engineers call the p-n junction. Instantly, some of those free electrons rush over to fill the nearby holes. This creates a really intense boundary right in the middle, called the depletion region. Honestly, think of this region as a massive, strict bouncer at a club. It creates an electric field that firmly says, nope, nobody else crosses this line. And here is where the magic happens. The sun is constantly firing down particles of light called photons. When a photon carrying exactly 1.1 electron volts of energy smashes into this junction, it physically knocks an electron loose. Suddenly we have a free electron and a new hole. But remember our bouncer? That electric field immediately shoves the loose electron up into the N-type layer. Now, because opposite charges attract, that electron desperately wants to get back to a hole on the P-type side. It can't go through the bouncer, but if we provide a VIP backdoor, like an external wire, that electron will zip all the way through our entire circuit just to get to the other side. That flow, that's electric current. That is how we get power. Okay, so we've cracked the quantum code. Let's look at section 3, connecting to the grid. How do we go from atomic movement to running an entire house? Well, one single cell only produces about half a volt of electricity. Not much. So we wire a bunch of cells together to make a module, what we all call a solar panel. Then we connect a bunch of panels into a string. And finally, we link all those strings together to build a massive solar array. It's just a giant hierarchy of scale, stacking microscopic power into massive grid-level energy. But we do have a slight problem here. Solar panels spit out DC, or direct current, electricity. The electrons flow constantly in one single direction, kind of like a steady river. Now, that's absolutely perfect for charging a battery, but your TV, your fridge, your AC unit, they run on alternating current, or AC power, where the electrons are constantly pulsing back and forth, much more like the rhythm of an ocean tide. To fix this, we have to use the unsung hero of the solar setup, the inverter. This is a box packed with lightning-fast electronic switches that rapidly chop up and alternate that steady DC river, perfectly faking that ocean tide rhythm to give us usable AC power. Literally, without the inverter, your home's electrical panel would have zero clue what to do with the sun's energy. And here's a fun fact. Because every inverter has strict limits on the power it can safely handle, we have to wire these panels up like a giant logic puzzle. Sometimes we wire them in series, daisy-chaining them to boost the overall voltage. Other times we wire them in parallel, which keeps the voltage flat but boosts the current. Usually, a big rooftop setup uses a very careful mix of both, so we don't accidentally fry the whole system. All right, let's jump to section 4, types of solar panels. Next time you're taking a walk around your neighborhood, look up, because you can actually tell exactly what tech your neighbors bought just by looking at the roof. Basically, there are 3 flavors. Polycrystalline panels are the ones with that shattered, flaky blue look. They're literally melted chunks of silicon, so the messy crystal structure drops their efficiency to around 13 to 17%, but hey, they're cheap. Then you have monocrystalline. These are those sleek, solid black panels. They are sliced from one single, perfect crystal grown in a lab, which bumps their efficiency up to 15 to 19%. And lastly, you might see thin film. Brown, flexible, super cheap to make, but a very random atomic structure means they max out at a measly 5 to 8% efficiency. Now wait a second, look at those numbers again. You might be thinking, 15 to 19%? That's the absolute best, highly engineered monocrystalline panel we can put on a house? That sounds incredibly low, right? Well, let's look at why that is. The culprit here is just the hard, physical limits of silicon itself. See, the sun throws a massive, chaotic spectrum of light at us. But remember our bouncer at the p-n junction? To knock an electron loose, a photon needs exactly 1.1 electron volts. If a photon hits the panel with too little energy, it just goes straight through like it wasn't even there. And if it hits with too much energy, that excess doesn't make more electricity, it just bakes the panel as wasted heat. Because of this Goldilocks rule, roughly 70% of all incoming solar energy is just straight up wasted as heat or reflected away. Pure silicon literally maxes out at a theoretical limit of about 30%. Honestly, it's an absolute miracle of physics that we can harness the sun at all, pulling free electricity right out of thin air to power our modern lives. But as our material science evolves, we are definitely hitting the wall with pure silicone. So here is the billion-dollar question for the next generation of engineers. How do we unlock that wasted 70%? Can we use new materials like perovskites to capture those lost wavelengths? Because whoever figures out how to engineer that next 30%, well, they're going to completely change the future of power generation on this planet. Thanks for hanging out with me for this explainer, and I'll see you in the next one.